The next part of this is the conservation of energy. Anytime there's a conservation law in physics or chemistry or whatever science you're looking at, that's a powerful tool because it allows you to predict the final outcome based on the initial outcome. Or if we know the final outcome, maybe we could backtrack and figure out what the initial outcome or what the initial conditions were. So there'll be all sorts of conservation laws before you're done sciences. This one we're talking about today is conservation of energy. There's conservation of mass, conservation of momentum, but we're going to focus on energy today. In words, the conservation of energy says energy cannot be created or destroyed, but it is allowed to be converted from one form to another. Before we go too much further, just sort of make sure I'm not leading you too far astray. Technically speaking, strictly speaking, the conservation of energy has a flaw in it. When Einstein did special relativity, he fixed it. There is a way that we can create energy. So we always used to say energy cannot be created. We now know how to create energy. We can create energy at the expense of mass. So there's a way that we could take mass, and usually it's like a nuclear reactor or a nuclear bomb through a nuclear chemistry. We can take mass and turn the mass into energy. So we can create energy, it just takes a lot of mass to do so. And the flip-flop is, if we had a particle with a lot of energy, like at CERN, those particle colliders you maybe read about where they discovered the Higgs boson and things like that, if we have highly energetic particles and crash them together, some of that energy will turn into new particles. We can actually create mass. So what I'm teaching you today is a little bit flawed. If we were to apply it to nuclear physics, it wouldn't work because we are actually allowed to create energy at the expense of mass. But we'll save that for grade 12. Here's my little thought experiment. Let's say you had a bowling ball at home and you held the bowling ball 2 meters above the ground and just held it at rest. If it's in the air above the ground, then it's got this gravitational field energy. But if you're holding it still, then it doesn't have any kinetic energy. If you let go of it and let it fall, when it's halfway to the ground, since it's lower, it's got a smaller height, its h would only be 1 as opposed to 2. If we cranked out the number, we would get that it has less gravitational energy. So this one would have gone down. But now when it's partway on the way down, it's moving, so it's got more kinetic energy than it did before. Its kinetic would have gone up, and its gravitational would have gone down. Let's do that in another color to make it stand out. If we think about the bowling ball, the split second it hits the ground, before the ground has a chance to stop it. Now it's at its lowest point. It's at its basically h equals 0, so it doesn't have any gravitational energy. It's decreased even more. But it's moving even faster than it was before, so the kinetic energy is increased even more. So we've got this transfer. It started off with gravitational energy, but as it fell, those joules of gravitational energy were converted into kinetic energy. If it started off, if we knew the mass and did sort of an MGH calculation, if it started off with 10 joules of gravitational energy and it wasn't moving, so it had 0 joules of kinetic, as it fell, the 10 should kind of stay the same. If it halfway down had half as much, that would mean the other 5 to make 10 joules would have to be kinetic. If when it hit the ground, now it's at its lowest point, so it doesn't have any gravitational, all of it is kinetic, the 10 joules would be kinetic. That's kind of how conservation of energy works. The joules will change from one form to another, but the total amount should stay the same. If you want to play around with it, actually you should play around with it, pause this video, go to this little simulation. It's a skateboarder and a half pipe, and if you click a bar graph, the bar graph will show the play between gravitational and kinetic energy. How as one goes down, the other goes back up. In simple terms, well, in as much as I want to talk here, that is the conservation of energy. Play with that simulation. There's some examples here to read through. Try them again, and then take a look at the worksheet. You should be able to do the rest of it, and there's a check-in question related to this as well. That's my little audio talk through of conservation of energy. As always, if you have any questions, email for clarification.